In our previous videos, we hunted down what a wave is and how it behaves. In this video, we will examine what happens when a wave interacts with another wave of the same frequency and resonates. By the end of this hunt, we will have a better understanding of how musical instruments produce sound. Good luck to everyone. A wave has its own frequency, amplitude, and speed. Previously, we saw how this wave interacts with media and how frequency does not change during reflection, but speed and amplitude can change direction. In this case, when we confine a wave's medium at its corners to reflect the wave will interfere with itself. Let's observe this on a string. Let the ends of a string be attached to a fixed wall. The wave reflected from this fixed end will change the direction of its amplitude and speed. Let's send waves with frequency omega, amplitude A, and speed v through the string. The expressions of these waves are given using trigonometric functions. This wave reflects back from the fixed point at the boundary. While reflecting, the direction of its speed and amplitude changes, and using this information, we can write the motion equation for the reflected wave as these two waves travel in opposite directions on the same string, so they interfere by their superposition. If we expand the trigonometric expressions in these equations using identities and simplify the expression, this expression is the superposition of two waves of the same frequency and amplitude that interfere with each other. As can be seen from this expression, the wave does not propagate because the sin kx term determines the positions of nodes and antinodes on the string, and these positions do not change over time. Since the wave does not propagate, there is no energy flow in the medium. The sign of omega t term shows how these points oscillate over time. So, do standing waves form at every frequency? To answer this question, we must apply boundary conditions. Since the ends of the string are fixed, the amplitude at these points must be 0. Here, x equals 0 and x equals L represent the boundaries of the string, which is the medium where the wave propagates. Since the string is fixed at these boundaries, the amplitudes must be 0. To modify our equation to satisfy this condition, we plug in 0 and L for x respectively. For the boundary condition at x equals 0, there is nothing we need to modify in our equation because the condition is already satisfied. Let's repeat the same process for L. In this equation, the expression sin e of 2 pi over lambda times L must be equal to 0 to satisfy the boundary condition. The condition that satisfies this is the angles where sin equals 0. According to this expression, for each integer n, a standing wave forms with different wavelengths. Wavelength depends on the wave's speed and frequency. Since the propagation medium does not change, wave speed remains the same, so changes in wavelength change the frequency. Thanks to this condition, the number n emerges. When n takes different integer values, the frequency and wavelength change to specific values. This shows that standing waves can only form at specific wavelengths and frequencies. In other words, the vibrations are discrete, or quantized. This n number is called the mode of vibration. The fundamental mode corresponds to n equals 1, and other modes are integer multiples of it. If we look carefully, different standing waves have different wavelengths and satisfy the node condition at different points. The frequency difference between modes is constant. While the n equals 1 mode is the fundamental, the other modes increase by a constant factor of this mode. Considering how frequency and wavelength depend on n, if we write the standing wave solution again, so by only changing the mode n, we can adjust the vibration frequency and wavelength on the string. So how do we control this n number? If an external force enforces the right points to become nodes, the standing wave equation will vibrate at the correct mode to satisfy this condition. Thus, we can control the mode at which the standing wave vibrates. The technique of changing the mode of the vibrating string in musical instruments is called flageolet. This will be one of the topics we will hunt down while exploring the science of music. Actually, the easiest way to adjust the frequency is to change the length of the string. If L changes, different frequencies can be obtained. This method is used in almost all instruments to tune the desired frequency. Now let's consider a different boundary condition. One end of the string is fixed, the other end is free. In this case, at the free end, amplitude is not 0, but the derivative with respect to position must be 0. Also, the reflected wave from the free end does not change the direction of its amplitude. We already know the motion equation of the incident wave. The wave formed due to the source wave and the system's boundary conditions may have an amplitude equal to either the opposite or the same as A, so we define a new amplitude B. Apply the boundary conditions and express B in terms of A. The sum of these two waves is the standing wave. If we simplify, our first boundary condition is that at x equals 0, the wave must have 0 amplitude at the fixed end. Let's simplify. To satisfy this equation, B must be equal to negative A. Accordingly, let's rewrite the standing wave solution. Now let's apply the other boundary condition at position L, where the derivative with respect to position must be 0. Let's take the derivative of the motion equation with respect to position and simplify. This equation is satisfied when cos kx equals 0, which happens at specific trigonometric angles. This trigonometric equality results in values where kl is the product of odd numbers and pi. If we isolate k and expand k, if we write the wavelength in terms of frequency and simplify, thus let's rearrange our standing wave solution again. With this example, we now know how to find solutions for any system with either fixed or free ends in one dimension. These examples will be very useful while hunting down the science behind music, so don't forget to stay tuned. Now that we know what standing waves are, in the next video we will examine what waveforms are, the properties that distinguish waves with the same frequencies, amplitudes, and wavelengths, and we will hunt down the Fourier analysis that solves this. Stay with science.